Morning, everyone. Welcome to the second tutorial in quantum mechanics. Okay, I will start by doing a quick review of linear dependency. Do you remember what linear dependency is? Okay, when we say that two things are linearly independent, linearly independent, not necessarily orthogonal. Everything that is orthogonal is linearly independent, but not every linear independent thing is orthogonal. Okay? So, we have, let's say we are in R3. Okay? Hey? Today is a very important lecture, so please don't hesitate to ask anything, either here in class or at home. Okay, so let's assume we have vectors in R3, right? These are vectors of the form A, B, C. Okay, so let's say we have a collection of vectors B1, B2, and B3. Okay, we say that these are linearly independent if if we have this equation. I'm going to put the hat here so you don't get confused. Okay.
Only if the scalars are trivial?
Right. If and only if A1 equals A2 equals A3 equals 0, right? Okay, do you want me to do an exercise on this, or it's clear? What does it mean?
You don't have to.
If this, do you remember that if these are three, if they are linearly independent vectors, they generate a space, a vector space, right? Everything is clear with that? Okay, we can move on. Do you remember what a linear transformation is?
Yeah, it's like matrix, right? So we multiply a vector and then we get the new vector.
Exactly. Okay, so a linear transformation is such that we have it's a transformation from a vector space to another vector space. I don't know if this notation is familiar to you.
Yeah.
If you want me, I can change it. Like these two are vector spaces, and a linear transformation is such that you come from one vector space to another. Okay? So, last tutorial, I told you that we can draw an equivalence between differential operators and matrices, right?
Yeah.
Okay, that's the whole idea in quantum mechanics. That's the basic, the basis of everything. That's the mathematical basis that supports the whole building of quantum mechanics. Okay, so the idea is we are going to start by saying that we have an operator. Okay, let F be an operator, and I'm going to use this notation. I don't know if you have ever seen this notation. It's an operator. I'm going to use this one, right? it's
Yeah,
better
yeah.
for me. Okay, I guess Richard also uses this notation, so it's going to be self-consistent. So how would you write? We know that all operators in quantum mechanics are linear. So what does that mean? This means that if we apply an operator to a vector, what do we receive?
A new vector.
Right. That's simple. We change from phi to this phi. Okay? And this is all there is to, like, this is the thing, this equation defines the operator. Okay? So, now let's start with a simple example. Okay? Okay, so why are these important in our formalism in quantum mechanics? Because every observable, everything that we can measure on a lab, is given by an operator. Okay? What do I mean by that? What can we measure, for example, in an experiment? What
Energy.
would you like to? Energy. Okay.
She said
Momentum. Position. Whatever. You can. We're going to see plenty of these things around the
What is
course.
QM?
Hmm?
What is QM?
QM, quantum mechanics. Okay? So, now, these operators are abstract things. Like, they don't have a well-defined structure until we assignate them a vector space in which they are. Okay? It's like, I don't know if those words mean anything, so please, if you're confused with that, let me.
You mean that it's abstract as long as we don't have a vector space for it to work on, right?
Exactly. Until we define the basis that generates the vector space on which this acts,
Yeah.
we don't have, like, these are abstract things. They don't have a well-defined structure. Like, if you want to write this as a matrix, if you don't associate the vector space on which these are acting, you cannot write a matrix. And this matrix is called the representation of the operator. Okay? We are going to be working instead of matrices with differential operators today. It will come the day that we are going to work as well with matrices. Okay? But for now, we are going to use differential operators. For example, use operators with Richard, right?
Yeah.
Can you tell me what is the representation of momentum in position space?
Minus IH bar W or
Right, great. Okay. So I am not putting an equal here. I'm putting this arrow because it's not that like momentum is always defined like this. It's that when we go to position space in X space, momentum assumes this form. Okay?
Although we can use it on a different vector space and then we'll get a different.
Exactly. That's the idea. This is very, very important and this lecture we're going to see why. Okay? That's the whole goal of this lecture and probably is the most important lecture of the course. Okay? So, what do we know about linear transformations? Okay, so there is a pretty important equation for this transformation. So you remember which equation? Like, if I want to get the properties of a transformation, which equation should I use? This is physical. Of course. Okay, so if we are in the time independent equation, we have the of the Schrödinger equation. Which equation is that?
The stationary solution.
Right, which is an eigenvalue equation.
Okay.
What is an eigenvalue equation? It's something like this, right?
Oh, okay.
This is like
How it's called?
eigenvalue. Okay? It's proper value equation. There are plenty of things. Eigen is in German,
Oh,
so that's the tradition. So what this equation is telling us? This is the most important equation in quantum mechanics. Right? Okay. So we have the eigenvalues and the eigenvectors. These are the eigenvectors, right? So look at the structure, right? We have a matrix here, and we have a scalar here. So what does that mean? Like, what does that even make sense? How can this make sense?
I mean, the transformation only expands the vector or redirect it. It doesn't change it like from its core or something.
Right, exactly. It doesn't. If you have like the vector space, right? A usual vector space. The eigenvectors are the ones that remain, that you only multiply them by a scalar. Remember that we are here working in the complex plane, right? Every vector has, like, lives in Cn. Do you remember this? Okay. So the idea is that it doesn't transform in the, like, you are not going to move the grid, like, okay, so let me show you very quick.
It would still be on the infinite line of the vector.
Right, right, exactly. Like, if we are in the real space, this can only be elongated. Yeah, exactly. Okay, so you get the concept.
Yes.
Do you want me to put the video, or it's okay? It's a very nice illustration that like everything moves, but the lines in the eigenvector. Okay, I will upload.
Maybe you can show us.
Yeah.
To you.
Thank you.
I knew I was underwater. I just didn't realize I was this underwater. If you're stressed...
Okay.
Like a scalar. For this specific example, the basis vector I hat is one such special vector. The span of I hat is the x-axis. And from the first column of the matrix, we can see that I hat moves over to 3 times itself, still on that x-axis. What's more, because...
You see the difference between what happened to the red vector and the green vector? Like,
Yeah,
the red vector moves, like, transforming.
And from the first column of the matrix,
And you
we
can
can
see
see
that
that
it
I hat
rotates, but
moves over to 3
the
times
green
itself,
vector is
still
only
on that
elongated.
x-axis.
It's only getting bigger.
What's
It's
more,
not
because of the
moving
way
with the
linear
green.
transformations
That's
work,
what an
any other
eigenvector
vector...
means, okay?
Okay.
The idea is that this vector, which is not an eigenvector, will move with the mesh, with the grid here. But this green vector, which is an eigenvector, will stay in its line. Okay?
Yeah.
So
It's like an invariant, right?
So exactly, like that's the idea. You have to think of this. These are like when we write this equation, we are generating a vector space, right? For each a, like little a, we are going to generate a vector, and that is special. That when we act with it with a matrix, instead of doing something very weird and moving, like you can rotate and elongate both of them at the same time, you are only multiplying by a scalar. So the vector space look pretty much the same after this transformation for only these vectors. Okay? So that's the general idea. Okay? So let's start with a simple example. Okay?
Can you please write on the left side of the board?
Sure.
Okay.
Sure, because
Because
I'm
you're left,
left.
so yeah.
Right.
Thanks.
Sure. Okay, but like this.
Thank you. Great.
Sure. Okay, so we have a P operator, and we are going to apply it. We are going to write the eigenvalue equation of P in the X space. Okay? As we saw last class, functions can be treated as vectors. Do you agree?
Yeah.
Okay, so what will be the eigenvalue of this?
P.
Right?
Side. P.
Do you agree? Because we are in the eigenvector space. So this is the same vector, right? It's not like we have here. That's a great thing about eigenvectors, that they remain the same. Okay? This is the idea here. The red vector, when they made the transformation, moves around, but the green vector, it only gets multiplied by a constant, so it's exactly the same vector. Okay? So let's use this representation since we are in position space. Okay? Okay, so this is the differential equation that will tell us the eigenvalues, the eigenvectors of position in position of momentum in position space. Okay, do you know the answer to this equation?
E to the I, no,
E
yeah, e to the I
exponent,
h, p over h.
So P of x is
exponent minus I bar.
No, p over h bar. But we get I because it's a minus 1 over I.
Here.
Yeah, we get minus 1 over I, which is I.
Right. So, do you want me to do it step by step, or it's okay like this? Right? Okay. So these are the eigenvalues up to what?
Space.
A constant. So, what do we know about functions in quantum mechanics? I'm sure Richard told. They must be what?
They must be complex if the average momentum is not 0. If that's what you mean.
No, they must be normalized.
Oh.
Since they are what?
Probability amplitude.
Distribution. Yeah, these are probabilities amplitude. And what is the probability distribution? How do we
The integral
get the probability?
We square it.
How do I square this thing?
This would be a squared because it's a complex phase, right?
Right. So
You do absolute value of the complex number and then you square it.
Okay, so how do I square complex functions?
Multiply it with the
Conjugate.
not the
Exactly.
how do I say it somewhat?
Okay.
Conjugate.
Huh?
Conjugate.
Conjugate?
You conjugate the
Yeah.
Right. Do you agree with this in general? Okay. So
but by definition, it would just give us, let's say z is a complex number, would have a plus ib. Then if you do the absolute value, it would just be square root of a squared plus b squared. And then you square it, you would just a squared plus b squared. Right?
right.
So
Okay.
we don't really need the conjugate. Because this is by Euler's identity would be sine plus cosine would be 1. Right?
Okay. Yeah, but let's go through that. So we want this to be. We know that every observable. I don't know if Richard told you this, but that every observable creates it, like its eigenvectors create a basis. Yeah.
Yeah. Huh?
Universal.
No,
The ortho.
without.
Right. Exactly. Like the orthogonality and like every. Okay. How do we know these are orthogonal and normalized, orthonormal?
I mean, wait, I
What
just
is
want a
this?
disclaimer.
Sure.
I studied only the linear algebra 1
Okay.
in my program, and this was taught in linear algebra 2.
But we saw it last class.
No, I remember the definition, right? The integral of the conjugative.
Right.
But I'm just saying that as a disclaimer.
Okay.
I
Okay.
wouldn't
Sure.
have any intuition.
Sure. Okay. Okay. So the idea was that it is always the same. It's we have our vectors. This is an inner product with vectors.
Yeah, okay.
So if you said it at the beginning of the class, if you have an orthogonal set of vectors, they are linearly independent,
Yes, this.
right? So they span a basis.
Yeah.
So this is what we're actually doing,
Okay.
like showing that these are orthogonals.
Oh.
Actually, orthonormal basis. What does this mean? That they are not just orthogonal, that when they are dot product with itself, it gives you 1. Because we want them to be a probability distribution and
Oh, okay. So they're like unit vectors?
just like that.
Okay.
So by definition, the vectors are orthonormal, right?
We make them we want to make them orthogonal always, orthonormal.
It's not by doing the linear transformation that makes them the
I think they would be
eigenvectors
orthonormal.
orthogonal.
Orthogonal, right? I think they would be orthonormal if A is the 1 over the size of the vector. And then you normalize that, right?
Exactly. Like, okay, if we have observables in quantum, in physics in general, have a special property that we are going to see in a couple of minutes.
Wait,
If we have this property,
observables,
observables.
can you define it?
Yeah, it's here.
Oh, okay.
Things that we can measure in the lab.
Oh, okay. Like measurable quantities.
Exactly. Observable. That's why it's a pretty bad word that they choose to put it like that.
Okay.
In the course I took in quantum mechanics, they call them dynamical variables. But I don't want to bother you with that term. It's horrendous.
Okay.
Okay? So let's do this. So what is the so can you please tell me how can I expand this?
Yeah, it's the integral from
Okay?
minus infinity to
Okay, I'm going to leave the
Okay.
boundaries.
of
This is just k.
Yeah, the
Right.
field k times field k.
Dx, right?
Yeah.
Ah, okay, yeah. What is this? We can put just the a square out. And okay. Right? Do you agree?
Yeah.
No. Step by step.
Where did the K come from? The K come from?
Okay, so this is k tag. I'm sorry.
Okay.
So, okay, I'm going to do it step by step. Okay, so we are going to take this e to the minus ikx times ik. This is tag x dx, right?
Ah, okay, okay.
This can be just written as I x k minus k tag dx. Okay, but what is this? If I put, I can
Change
multiply and divide by 2 pi, right?
okay.
And this is 1 over 2 pi, the integral e to the I k minus k tag x dx. What is this?
That's not a one. I mean, it's not a normal distribution.
You should know what this is. We talk about this, don't worry.
Oh wait, that's. Oh.
I present you the delta function.
Ah,
Yeah.
Okay? So we have that this is 2 pi delta, but in order for this to be orthonormalized, this must be only the delta function, right?
uh-huh.
So what's the value of a?
1 over square root of 2.
Exactly. So a is 1 over the square root of 2 pi. But I can put here an I to the theta. Do you agree? Why can I do that?
It's like a phase, you can expand it. Because
What happens if I put here like this? Then a complex conjugate would be I to the minus I theta over the square root of pi, right?
yeah.
And what is this?
Oh, you'd still be with, okay, yeah.
So this would be 1 over 2 pi. Since I am going,
I mean, physically, it just means that the initial vector would just be in a different direction, but would still be, would still stay in the same position.
the actually reason is that physically, the phases doesn't mean anything physical. A general phase, anything that multiplies a wave function by a factor of like this,
Yeah.
doesn't have any physical meaning.
So what does it?
So if I multiply by it, I don't change the physics of the system.
So why do we need this factor?
No, we don't need it. We can choose the factor that we like.
So
That's a
why
great
does
thing.
it appear? I mean, in waves and stuff. Why does this factor appear?
No, if we have this factor for all the wave function, if we multiply by the full wave function, I'm going to put here, it doesn't change the physics of the problem at all. Like we can define the new
Why
f
does it exist?
type. it's okay. In more advanced courses you will see, but this is a symmetry of the system. Like you can pick whichever theta you like, and the physics will remain the same.
Oh, so it's the symmetry around the theta.
So what does that mean in our language? I have a perfect example, since you have, of course, already done the homework, right? So the Fourier transform of my function, I can multiply it by a phase, and I know that if I do the Fourier transform of f of x plus x naught, it will just give me e to the x naught
ik
f and the Fourier transform ikx, right? X naught, the Fourier transform of f of x, right?
Yeah.
What is this telling me? That if I start at x equals 0, or if I start at x equals x naught, the physics are the same. I can choose my origin of coordinates wherever I want.
Oh. Okay.
Do you see it?
It's like the. Is it like the arbitrarity of defining potential or something that I can start whenever I want?
You can put it wherever you like. Exactly.
Okay.
That's exactly the same. Do you see it? Or okay. So I will continue.
Can I?
You can check the recording as well. Okay.
But please, if you can write on the left side.
Sure. Sure.
Thanks.
I
Wait,
will.
don't erase it.
I will keep writing like this. It's okay.
Okay.
Like, we will give you a space. So what do we know? Like, we can now define x, the phi. We know what a is now. It's 1 over 2 pi. I spoiled myself. This is phi of x. Let me define.
And that's what we've seen last week.
So what is this?
This is the unit vector you said.
Okay, but this is a Fourier transform, right? It's the nuclear.
Yeah.
It's the kernel of the transformation.
Yeah.
That's what I wrote here. Like if you change your position, if you shift your position from 0 to x naught, you will remain with the same momentum. That shouldn't change your physics at all. So this thing is the, so if we want to move from position to momentum, what we have to do is just do a Fourier transform. Okay, so now what is it? Okay, so now that we have a well-defined momentum, okay, so do you remember this from modern physics?
Okay.
No? This is a very important equation. I'm sorry, I didn't put it here. You see, I assumed that you know it here, and you didn't ask where the h bar went.
Yeah, and P.
This is the wave number. This is the de Broglie.
Oh, okay.
I think it's spelled like this, but don't put a lot of emphasis on that. Okay? I need to start speeding up. Tell me if I'm going too fast, too slow, too anything. If you have any questions, please don't hesitate to ask. Okay? So we had our phi of x, phi of k, 1 over 2 pi I k x, right? So how can we know the probability? We want to know the probability distribution in the position space. So what does that mean? We want to find the probability distribution of where the particle can be. How can we do that? P of x of t is what? In this case, we can forget about the t because we have no explicit time dependence. Okay? We saw it like a couple of minutes ago. It's just like this, right?
Yeah, it's just
Now we're doing the probability.
Yeah, now that we have the momentum distribution, like the eigenvalue, if we have a well-defined momentum k, I'm going to exchange momentum and k, because in quantum mechanics we saw that they are equivalent, right, up to a constant. Yeah? It's okay?
Yeah.
You're going to get, the idea is that you get used to it. Okay? This is x. Okay? So we have a particle with a well-defined momentum. What can we say about the probability distribution in position? So if our particle has we know the momentum of the particle, what happens to the position? Let's see. Okay, so we know that this is 1 over 2 pi ikx ikx. Okay, but this is what? This is just 1. It's not delta
Right. No.
because we have well-defined k. We know exactly what k is, right? So this is 1 over 2 pi. So the probability distribution is a constant. What does that mean? That the particle, the position of the particle is not well-defined. Every point in space has the same probability to be, that the particle has the same probability to be in any place, in any part of space. So this is the first side. I am going to make a presentation. Students, Heisenberg uncertainty principle, Heisenberg uncertainty principle, students.
Oh, okay.
You have already, you can meet there. Okay, we are going to talk a lot about this lecture. Okay, now, if we are going, now we want the eigenvalues, the eigenvectors of position operator in position space. Okay, so what does that is? X of x equals x naught psi of x, right? Can you tell me what is the eigenvector of this equation? This is the eigenvalue equation for the position space.
But the position operator just stays the same, right? Which is
Right. Okay. So, what is the position operator? I jump a step. In position space is just x, right?
Yeah.
What is the eigenvalue of a position? Well, just some position that you like, whichever position. And we have the same eigenvector. Which function you put an x and gets you a value, and a specific value?
I mean, you can have a constant, right? That every x is sent to x0.
No, because if this is a constant, okay, if this is a constant, you cannot shift the position to.
No, not the x, but x. I mean, the function x.
No, x is that function. That's the representation. You cannot move that. This is the representation of this operator.
No, I know, but I mean that x would send c to. Okay. No, okay. I think I understand what you're saying.
Okay, what function? Okay, you can think like that. Okay, which function will do something that every x will give you just one value, and all the other values are not going to appear. Are going to be 0. Okay, this sounds familiar? If I put here the delta function, when I integrate around this, it will only give me this value, x, right? Do you agree?
Yes.
Okay. So let's talk about Hermitian operators. Okay. Okay, Hermitian operators are defined like this. Okay, let f be an operator. Okay, then if f is Hermitian, then we have this property. Sorry. What does that mean? That I can act on the right side, like on the function on the right, or I can act on the function of the left, and I will receive exactly the same thing. The integral will be the same. This is the definition of hermicity. This is a definition. Okay? Why is that the case? Why all observables are Hermitian? Because we don't want, like, we can decide in which space of functions we are going to expand our basis, right? And we know that the things that I can observe in the lab are operators. So I don't want that if I act on the complex conjugate of the function, or if I act on the normal function, that changed me the physics of the problem. I always want that to have the observer that I can choose which function I'm using. Okay, which I don't need to, like, it's the same if I use the complex function or if I use the normal function. I'm going to explain myself 1 second. Okay, so if an operator satisfies this equation, that means that its eigenvalues, do you remember the equation?
Yeah.
Are real. I don't want my position to be imaginary. I don't know what that means. So I must enforce the condition that everything that I can put on a lab, it's Hermitian. Okay? Sounds like logical assumption to make for you. Okay. This is one of the postulates of quantum mechanics. We will talk about them in a couple of lectures. Okay. So properties. Okay. This is the first one, which I just told you. Right? If f is an Hermitian operator, then its eigenvalues are real for every f. Okay. Then I also told you this property before. The eigenvectors of an observable are orthonormal. I can prove this, or I can give you homework. I'm going to give you homework. If I don't give you homework, you're going to get bored, and I don't want that. You see, I'm always thinking about it. Okay? So we saw the case, right? Do you remember that it was delta function? Yeah. Position, of course, is unobservable. So, yeah, prove by example. And the other thing is that the eigenvectors of an Hermitian operator form a complete basis of a Hilbert space. Which, as we saw, is just the vector space of functions. It's the equivalent of having a vector space but with functions. This is what Hilbert space means. Okay?
What do you mean by a complete basis?
That, okay, if I have two vectors, do you remember the example of R3?
Then you can,
if I have two vectors only, I cannot produce every vector in R3.
so you can present,
I can only put it, I can only generate a plane. I need the third vector to generate all the other vectors.
So you mean that you can present
Right?
every vector in the vector space as a linear
Combination, exactly. So that's why we talk about linear combination. It's not that it was completely disconnected to the.
And here you took the conjugative of the operator of side in the
Right. So the property defining, like another way to, do you want to see here? Like the great thing about Hermitian operators, this is complex that this diagram here means you are going to transpose a matrix and complex conjugation, okay? Which is the same as you will think as conjugation. Okay? This is the thing defining Hermitian operators. That its complex conjugate version is exactly the same. Like, this is what we are saying here. No matter if you act in the normal space or in the complex part of the space, I'm referring spaces as the ones spanned by the functions, right? If you have any questions in terminology, please let me know. Okay, but it's the same if I act on the normal and on the complex version of that space. Okay, if you want to read more about that, it's in mathematics it's called dual space. Okay. Yeah, I'm going to leave you this part.
So can you rewrite please the complete basis of You said that the Hilbert space is a space of when we
of functions
regard functions as vectors.
that has inner product. Okay?
Okay.
You know what?
Product. This thing. Okay? So, example. Let's prove that momentum is Hermitian. You see there, my Mexican accent went crazy. Okay, so we know P has the representation, right? So let's integrate this. What can we do here? So for me, I just see only one option, integrate by parts, right? If you have the derivative of a function times a function, what do? Integrate by parts, right? Okay, this is for the whole thing, and this is the x for the complex one times ci of x. Okay, right? What do we know about this guy? What is the probability of finding the particle at infinity?
0.
At minus infinity?
Also 0.
Okay, so this is 0. Do you agree? Agree? Excellent. So what do we? I have a minus here, right? So I can put AH bar d dx complex conjugate times dx, right?
Inside the
I can put it up again inside this thing. So this would be the integral of IH bar d on dx times the complex conjugate times the function p of x. And what do I have here? None less than p operator complex conjugated. Like I have this thing. Do you agree?
Yeah.
Which is what I wanted to prove, so I'm happy. Okay, great. So we saw a lot of operators, and I'm going to write you a list. I'm sorry. Everything is in the tutorial, but sure. I should start erasing the part that I don't just write, right? It would be a good idea. Sorry, this is a very exciting topic for me, so I get. This is psi. This is okay. IH bar. I'm sorry.
Oh, it's okay.
Right?
No, it should be minus h bar and then minus h bar.
You're right.
Okay. Now,
You know, elementary school mistakes are the worst ones. Okay? So, more operators. Can you please tell me what is the representation of the kinetical energy? In position space.
I mean,
What is kinetic energy? It's like this, right?
Yeah.
Do you agree?
You can see.
Sorry? This is not. This is. I haven't chosen a basis, right? So I can put an equal. Now I'm choosing a basis. Okay. And this is h bar squared minus. Right? Do you agree? Yeah?
Y minus
You don't see it?
I square is minus 1 and 0.
Right? So I did.
Yeah, I know.
Yeah?
Yeah.
Great. Okay. Another one, you saw this one with Richard. I'm going to put, what is the energy?
I
IH bar dot dt. Okay, so yeah, you get the idea. And I can put more. We are going to meet them in the course.
Wait, can I ask you a question?
Sure.
The second property, why does it have to be Hermitian operator? I mean, we saw last
No.
presentation that we just, by the definition of an inner product, we get this property. As long as we use the Fian like we used the...
No, we saw it for a specific function.
Yeah.
This specific function, you see, comes from this operator, which is Hermitian.
Oh.
Right?
Now if it is Hermitian, we can expand it to every...
I am not saying that all the bases come from Hermitian operators. I am saying that for all Hermitian operators, their eigenvectors produce an orthonormal basis. It's different. I am not saying every orthonormal basis comes from an Hermitian operator. I'm saying, yeah.
So the fees are not necessarily the functions we've seen.
No, it
can be okay.
We are going to meet a lot of fees this
And what is the notation of the line and then the...
This?
Yeah.
Okay, this is Dirac notation. You see, I put this vector, phi n.
Yeah.
This is a vector. This is the other part of the vector. This is called a ket, and this is called a bra. So this is a bra ket.
Okay.
And this is inner product. This it means we saw it last class. It means like
no, the inner product I understand, but what is the in the three property?
Right.
The third property you just wrote only one side of it. So what does that mean?
We're going to see that. Okay. For now, you can think as functions. Like if you have, I don't want to get into the details, but this produces these things. Just as operators are not defined until you put them a basis, these vectors are not defined until you put them a basis. But I don't want to get into that thing. You can write this if you prefer here. Okay? I can erase this. Okay. So we know the probability for a particle is like this, right? How can we go from eigenvectors in position space, like functions in position space, to functions in momentum space? Great. Right? So, what is the probability of finding a particle at a certain momentum at certain time? What do you think?
What?
We know the probability of finding a particle on a certain position at certain time, right? What is the probability of finding a particle at certain momentum at certain time?
The same way with the psi wave. No?
Exactly. We just put a hat. Great.
this is a vector of, wait, a basis of, okay, a vector of functions, that it is the complete basis of a space of the entire functions we can create.
Yeah.
So it's like if we use cosines and sines, and then we use Fourier transform, and then we,
Every time think it like that.
okay,
We have cosines and sines, and we can put any function there, and we
Okay.
can expand it as a Fourier series.
okay,
It's just like that.
okay,
We're going to see that Fourier series is just an example.
oh, okay,
Okay?
perfect. And it works for every function in the vector space we are talking about.
Again?
It would work for any function in the vector space that we are talking about.
Yeah, definitely. Okay, so let's go to expectation values. Okay? So, if we have an operator f, right? Then the expectation value of f is nonetheless this integral. Okay, I'm going to use another step here, sorry. Okay. Okay, so the
So now it
expectation
is-
value is this thing, which we don't know what it is. It is defined like this. Whenever I mean this thing, I mean this integration. Okay?
It looks like this means it's a mod.
Right.
The left one.
Right.
Right?
You put it's not like, of course it's not by accident. Like this thing and this thing look very similar, and this thing is just the definition. You know, when you have when you want to do an average in probability, you take the variable you want and multiply it by the probability distribution, right?
Yeah.
This is just what we have here. This is our probability distribution, our amplitudes, and this is what the variable that we want to average, right? It's very like straightforward. Okay, let's take the Morse battle. Our example will be e to the minus alpha x. Okay. So exercise. I'm going to change the color. I noticed that I haven't done that for a while, and that may be confusing. Okay. We must find, we're going to learn a nice trick, an integration trick today. We must find x squared p squared. Right? This is the exercise. This is the statement of the problem. Okay? So let's start with the solution. Don't worry, for these properties you have plenty of homework to do to understand.
No, I don't. Can I ask you a question just
Sure.
behind? The intuition about an operator being in remission would be that if I transform it like linearly on the conjugate of it, or either on the conjugate model of it and the regular one, and I multiply them, it would say the same.
I'm going to tell you like the mathematical version. It shouldn't matter what do you choose to be the complex conjugate of what,
Okay.
right? It shouldn't matter. You can choose the what is the complex conjugate to what.
Yeah.
And so in the same spirit, it doesn't matter if you are going to observe something. It should be the same if you operate it in one vector space or into the other, right?
I mean, but if you look at the conjugates in the regular one, the vector space doesn't change, right? So how is that working?
No, they are different vector spaces. I don't want to get very into that. These are called dual spaces.
Okay.
It's just the projection. If you have a vector,
Yeah.
it exists a vector space. There exists another vector space, such that if you make the inner product between two elements, this will be a scalar.
Okay.
So this is the definition of this would be a dual vector. You can choose whatever you want. I don't want to get into because it's going to be mathematically annoying. But the thing is that these are not necessarily like, it shouldn't matter what do you choose to be the complex version or the non-complex version. So you should get the same. The real intuition of Hermitian operators comes from its eigenvalues. Okay, that is the main thing. Its eigenvalues must be real because I don't know a position that is imaginary or complex.
But shouldn't that mean that the vector, on its own should not be complex? Because if I want to write
No, I just proved you. You are going to do that. So I show you the value. So the expectation value is always this is very important, okay? If you get a complex momentum, a complex position, anything, you know that you screwed up in something. Richard cares more that if you have, for an example, if you get an imaginary position, okay? Richard cares more if the calculation was slightly wrong, but you still put imaginary position, he will put you 0 on that. If you put him, I know my calculation is wrong because I receive an imaginary position, he will give you most of the points in the exam. So that's a pretty important thing to notice. Okay? So let's go to this. And we can discuss the mathematical insights of quantum mechanics. It's my favorite topic I ever learned in physics, so whenever you want. So, first thing, 1. Someone know the answer to this? Like straight away? No? Okay. So, alpha is bigger than 0. Alpha is bigger than 0. Okay? In order to converge. So, we have the complex conjugate of this function is just this function. Do you agree?
Yeah.
Okay. So what is the representation of this operator in position space? X. What is the value of this integral? Now, can someone say from minus infinity to infinity? Why?
I mean, I did the integration by parts, right? And then the exponent is 0 at infinity and minus infinity because it's an even function that decreases.
Right. Okay. So if you integrate over minus a to a, this is an even function, right? And this is an odd function, right? So this total function, what is?
Oh, odd and then 0.
So this is 0. Right? These things, you must look at these things. Like it's going to help you a lot in your calculations and go very fast in the exam. I think this. So we are going to learn one of my favorite tricks in quantum mechanics. Like, it's not for quantum mechanics, but it's used a lot in quantum mechanics. This thing. Okay. So I'm going to just write it like this. This is 2 alpha. Right? Okay? I'm going to show you a nice trick to solve this integral. Okay? First, we notice that everything here, that this is an even function. Even function with even function is even function. So we can write 2 times minus to infinity x squared e minus 2 alpha, and I can get rid of the absolute value. Do you agree?
Yeah.
Yeah? Okay. So what can I do?
Integration by parts.
Twice.
Okay.
Twice.
Okay. We can do 2 tricks here. I'm going to show you a
Okay,
nice.
no, this-
yeah, we can do it once and then we get this.
That's not true.
Huh?
This, you mean 0?
We can do partial integration once.
Okay.
We have this.
Okay.
You know?
This is a bit different because we have here the x only, and not the second
Yes,
one.
but if we do partial integration once,
One, right. I agree. Like, you can do that. X squared, you see, if I, let's define beta to be 2 alpha, okay? Okay, if I derive this twice, this function twice, as a function of beta, what do I receive? Right? This is just it. Do you agree? No?
No, you do. It just takes me time because you're right.
Sure.
So
Sure. Sure, of course.
yeah, it,
You can shout me. Oh.
you want me to? I will.
Sure.
Okay.
Take delivery. Okay? So, what if I, instead of putting this, I put just this, right? Partial derivative. So it's not. It's also a function of x. Okay? Right? Do you agree? Now I can exchange. Right? And I will have 2 times the beta, the integral 0 to x of e minus x of beta x dx. What is this? Right? This is 2 and beta squared. This is what? 1 over minus beta. E to the minus x beta x from 0 to infinity. So what happens when b go to 0?
1 over beta. I mean,
So,
minus x over
First, what happens at infinity?
0.
Right? And at 0,
It's 1 over beta. It's minus, so it's 1 over beta.
e squared. It's a minus, so it's 1 over beta. So we just need to derive this twice, right? A nice trick. So what will be the first derivative of this?
Minus 1 over beta. So it should be 2 over b to the power.
Now, what is the second derivative of, like the derivative of this?
It's 2 over beta to the power 3.
2 over beta.
I think. No, but another 2, it's like 4.
Right. To the power 3.
And 2 over beta.
This is
4.
and this is 4 times, and what do we say it was beta? 2 alpha.
Over 8 alpha. It's 1 over 2.
I'm going to raise
alpha.
this. So this is 4. 1 over
8
8 alpha cube, which is 1 over 2 alpha cube, right?
yeah.
Let me see that I had the same result before. Yeah, great, with one exemption. You see, you didn't tell me I forgot the a all the way from here. So we can agree that I can put just a squared here, right? So I can put a squared here,
Yes.
okay?
No, no,
So do you like this trick?
Yeah.
This is called Feynman integral trick.
no.
It's very useful for quantum mechanics. So now what we want to do is to calculate now the momentum. I'm going to just leave this thing. I'm sorry, can I erase?
Yeah.
So sometimes it's more annoying than integrating by parts. I am going to show. I want to show you another trick later on, if I have time, which will do integrating by parts this kind of functions very easy. So this would be the x squared. Okay. Now what we want to do is the momentum. Okay? There are two, we can do it in two different ways. Okay? What are these ways? Okay, we can use directly the operator, or we can change our function to momentum space, and there in momentum space, I didn't tell you. Okay, let me just put momentum space, position space. Okay, in momentum space, X assumes the form of IH bar D on dP minus, and P assumes the form of P, and in position space this is just X, and P is what we saw, which is IH bar D and dx. This is a very important. You see, this is what we saw. It depends which basis are you operating in. You will receive a different representation of the operator. Okay? So we can do that. We can go to momentum space and shift the psi of x would be 1 over 2 pi, the integral from minus infinity to infinity of e alpha x I to the minus kx dk. So, since you are experts in Fourier transform, let me just tell you that the bottom line.
Now we're going to the momentum space.
Yeah. We can, of course, just derivate once and the function. Okay, but I want to show you this at least once. Okay. So this is now our function. This is phi of k, which is the Fourier transform. Okay, everything is clear.
What did you write on the integral d minus alpha what?
Alpha absolute value of x here.
There's no k there? Ah, okay.
This is this is the kernel.
Okay.
This is the kernel of the integration, like the part, the thing that defines the Fourier transform.
Ah.
You know, I'm going to put this. If something is going to stick to you in this course, is this relation. Okay. So
This relation is in momentum space.
this thing.
No, the p equals h from k.
Yeah, sure. You're saying that this is actually the same space because it's up to a constant, right? You're saying that momentum and the wave number of the wave function are related up to Planck's constant.
Yes, I'm asking if I can use this in space. במרחב מיקום ומרחב תאנה.
כן. Okay, sure.
I think you should say,
Sure. She asked me if you can use this in momentum space. What should you do? You do this. D on dp is just d on dk dp. D on dk, right? Do you agree? This is the chain rule. It just
Yeah.
But I know that k is p over h, right? Or h bar. Yeah. So when I derivate this, I am just going to be left with d on dk, right? Which is just the on the h bar k, which is just. It's a pretty annoying way to write one.
Yeah, it's a general rule,
אנחנו
right?
עוברים עכשיו ממרחב מיקום למרחב
the auto. Okay, she's asking if it's the same space. I am saying it's the same space because if you define the vector B and you change it to a vector A, like to a vector W, this is to a vector B. This stills on the same line. The only thing you did is that you make bigger this vector, right? Instead of having this, you change to have this. This is B,
Yeah, I understand
and
that.
this is. So it generates the same vector.
So I can use this equation for both spaces.
Yeah, of course. Whenever you
It's
want.
a general rule, right?
Yeah, it's one of the foundations in quantum mechanics.
But can I ask you a question? Now K in the Fourier transform is not just like a general argument to the function. Now it has physical properties, right?
Right, of course.
Because it's now like the momentum. It's a
Right.
representation of okay.
Exactly. That's what we showed when we showed that the way to go the eigenfunctions of momentum in position space are just these things.
Yeah.
Right? That's exactly what we showed. The physical meaning of the Fourier transform.
Okay.
Great. So let me tell you that. Okay, so this is now our function. You agree this is an even function,
Yeah.
right? Because so if I evaluate phi of k, it's exactly the same of saying phi of minus k,
Yeah.
right? So the expected value of momentum, it will be 0, right? Why? Because we're using this thing. Since we are in momentum space, we use the representation
Oh,
of
okay.
P.
Yeah. Okay. So
Okay.
it's like dx.
This is dk. I'm going to substitute this. Okay. Yeah.
Yeah, like.
Put P. Okay. And this will be 0. Just like that. Let me tell you the bottom line because I see I have no more time. So, this thing, it's going to be h bar a square alpha, okay? And now we're going to go to the uncertainty principle. We're going to define it, okay? Just give me just 7 minutes. I will go to the uncertainty principle. Right, but exactly. Okay. Yeah. So you know what this You're right. Okay. What does the uncertainty principle tell you? This, do you agree that this tells me how spread my function is, right? Yeah. Okay. How much? The idea is that idea is that you're going to get this in the homework, or I don't know if in this one or the next one. But if I have a function in position which is like very well spread, in momentum, which is x, in momentum, like my momentum variable will be very sharp. Yeah. Okay? So the more I know about my momentum, the less I know about my position, and conversely. Okay? So how can I express this? This is expressed by a formula of this form. dx dt is h bar over 2, I guess. Yeah, sure. Okay. So, what is the value of delta x for our case? What's the value of this?
0.
Okay.
The value of that.
Is the value of this, right? The square root of this, which is a over the square root of 2 alpha 3/3, right?
Yeah.
And what's the standard deviation in momentum? The uncertainty in momentum?
A absolute value of it times square root of 8 for all.
Let me just 1 second. Let me see that. Okay, now we want to know what's A, right? How can we know what's A? Right? We agree? This must be equal to 1. Right? Since the wave function is equal to 1, the yes, sure. Square. So we can say square. Okay, so just the same as we did, right? This will be alpha. Okay? So this must be equal to 1, that means that A must be 1. So let's go to the disorder here. Square root alpha, right? This is just h bar. This is square root alpha, right? So let's do calculation. Right? So this one is here, right? We have alpha squared. So we have a squared, right? 1a and 1a. Okay, we have h bar. We have alpha. This, right? H bar. No, H bar. 3 times 2, right? Okay, so this will be just H bar. What is this? This is just
Yeah, 1 half the square root of 2.
this is alpha 2 square root of 2. This is alpha 3/3, right?
Oh,
Agree?
yeah.
And this is H bar over the square root of 2, which is bigger than H bar over 2. Therefore, the uncertainty principle is satisfied. It's happy. Okay?
So if we don't get the uncertainty satisfied, then either we made a mistake or the resistance.
Exactly. Most probably you did that.
Yeah.
Okay? Any of your, like, this is, you know, they try to put very important physical concepts against the uncertainty principle. For example, the conservation of energy is broken under uncertainty principle. It's harder to break the uncertainty principle than to break the conservation of energy. This is how huge this thing is. Like, it's one of the most strong results in the history of physics. Okay? Why did I was so worried that alpha was cancelled?
Why?
Yeah. Exactly. Then we can choose. We can arbitrarily pick alpha in order to the system not satisfy the uncertainty. So when you get something like that, you see you are making some mistake, so you have to go back.
So you should not be depending on a parameter.
Exactly. It should be a constant that you can compare with H bar over 2, and it must be always the same. Okay, so do you have any questions on this, on Richard's material, anything you want to ask? Everything you can watch on this man. All the videos I posted too, and I'm going to post this one as well, are complete from this series. You see, that's great videos on Earth-Plans, on linear algebra, eigenvalues, everything. Anything else?
Wait, are you uploading recording this recording now?
I don't know if right now, right away, but it
I
should
need
be.
to make up some very, like I missed some materials and I want to sum it up.
Okay, sure.
So I want to know physically. You can stop the recording.
Sure.